Hey everyone, thanks for coming. My name is Michael Fischer. I'm a research scientist at Adobe Research, and I'll be talking about the work we do, or did in this case, on material selection in 2D and also a little bit beyond that. First of all, a little bit about me, because maybe people don't know. I'm from the south of Germany. I studied aerospace engineering in my bachelor's. I did my PhD here in London with UCL, had two amazing supervisors, Tobias and Niloy here. Did some internships at Mitra and also Adobe, where I work as a full-time research scientist now. And this year actually, in March and May, I got the Eurographics PhD award for my PhD work, which I'm very proud and very grateful for having received. Okay, so to get into the talk, I brought a little motivating example, because this is the thing you will be tormented with for the next half hour. We talk about material selection, and usually what we mean by that in this context is going to be an image. It's a little bit hard to see here maybe, but there's a click here, right? So user provided click and an image, and the output of the algorithm that we want is a mask, a selection mask, where all the pixels that have this material, regardless of differences in shading, are selected. And I have to apologize for the differences in mask color and click color and convention, because these are results extracted from papers that we published over the years. And as you can see, we weren't very consistent, and we changed the conventions a bunch and so on. So sorry about that. The definition we use for materials is in the appearance domain. So we say a material is a pattern with the same surface texture and reflectance properties. And notably, this is different from material classification, right? Because for example, in this room, it's actually a bit hard to see, bad example. But you have, for example, a white wall here, and you have a white chalkboard thing here, and obviously those are not the same material, right? And so we have that same definition. You can have different types of woods in an image, but they would be classified as separate material depending on where the user clicked. Now, what it's not segmentation, it's not classification. We don't yet do generative models, but we're gonna get to that later in this talk. And as a preface, I want to briefly outline why this is a hard problem, right? In the natural world, humans are very good at talking about materials and distinguishing materials, because we interact with them every day, and they're governed by their response to lighting, viewing directions, their material properties like roughness and so on. But as soon as you take a rendering or actually a photo of an object in the real world, you collapse all this information into only 3 pixel values, RGB. And for a machine, it's very hard to reason from just 3 values about what a material is, right? And actually on this car image, if you take a color picker in Photoshop and you click there, this is the color you get. If you click down there on the chassis, this is the color you get. Obviously it's the same material, but this part is in the shade. Similarly, if you do this for the highlighted part, you again get a very different material. Obviously those are very different colors, yet the machine should understand that they constitute one material. Now, I want to briefly outline those 5 works in this talk. I hope that this is going to be interesting. I hope that there will be lessons learned and takeaways for other fields, because obviously not everybody is working on material selection, but I hope that I can inspire some research based on those principles. And I hope it's not going to be boring. I promise I won't have big tables and scary math and stuff, because it's not the right time. It's way too late in the day for this kind of stuff. All right, so this is the first paper I want to briefly outline. This is materialistic from SIGGRAPH 23. And this was a bit seminal in the way that it defined this task of material selection using deep neural features. Again, same definition. Materials are the patterns with same surface texture and reflectance properties, regardless of shading variations. You can see it on the castle. The colors are very different, although the same material is selected here. And how this works, from today's perspective, is relatively basic, but at the time this was a bit, kind of a new thing. Sorry. Okay. So here again on the left you have your input image, user provided click. You simply take the dyno embeddings, and you have some learnable projections that massage these embeddings into something that's useful for a selection algorithm. And then you use those embeddings as the keys and values into a cross-attention mechanism. Now, because we have this user-provided click, we know which material the user wanted in the image. So we can get a similar embedding, but just of this click or of the patch that the click was in, and can use this as a query, right? And in attention, keys and values tell you what stuff is, and the query tells you where stuff is. So if you compute the attention mechanism, you will get this selection mask. Now, Dino obviously contains very rich priors because it's been trained on internet scale data, and those transfer nicely to material space, as we learned. And these cross attention that we do here allows you to have like open set queries. Basically, whatever the user wants to click on, we are now able to select. The cool thing about this architecture is that nothing forces you to use the same two images, right? The upper image could be this image of the Arc de Triomphe in Paris, and the lower image could be something entirely different, but you can still get the patch embedding, and you can still get the right selection mask for the upper image. So the way we trained this thing back then was we rendered out a bunch of synthetic data from Blender. I think our internet at the time took like 50,000 images, or a bunch of scenes, and rendered 50,000 images of them. They have dense material annotations, so each click has a dense mask associated with it. And the important thing is this is all synthetic renderings, but because we have the Dino backbone frozen, it generalizes nicely to actual natural images. And the maybe a bit ironic thing is nothing here is specific about materials to the architecture. It's purely in the training data. So this is, I guess, the lesson number one, the takeaway. In the days of attention mechanisms and transformers, it's all about the data. I think this is a motto that aligns very nicely with a talk for Voxel 1, because as you will hear from Harpreet later, this is pretty much what they do. So we will see this lesson maker come back later in the talk. All right, so very briefly only, this was the second paper, fine-grained spatially varying material selection. This was presented at SIGGRAPH Asia 25, and because it's a mouthful, we just usually call it materialistic 2. Yes, sorry, this clicker is not very responsive. Okay, so in materialistic 2, what we did is we realized that the definition of a material depends on the scale of which you look at it, right? Imagine a bark of a tree. If you look at it on like a microscopic scale or a mesoscale, it's very different than if you look at it from far away. It changes the reflectance properties and also its appearance. And it's the same with many images that you have in the real world. Here, for example, in the dress, if you click here, would you want to select just this blue flower, or would you want to select the entire dress? And with the same definition of materials, we just add a level of like closeness or of scale. This paper now allows us, or this project now allows us, to do like selections on 2 levels. The first one is what we call the subtexture level. So here all the blue flowers are selected. This was the previous algorithm, by the way. And the second level is like the texture level, where you can include spatially varying patterns in your selection masks. And once you start thinking about materials that way, you will realize that almost all the images you see in the real world have this property. So this is something very natural and very useful to exploit. Also from like an artist, from a user perspective, you always want to be able to have this 2-level support. Now, I said I'm not going to go too much into like the architectural details, so this is going to be very high level. If you want multi-level reasoning, multi-level selection, you of course need multi-level processing. So we reused the architecture for materialistic 1, embedding into Dino features, projections, and so on. But now we do it on, first of all, the entire image to get like the global context, but then also on the 4 different tiles of this image to have like more resolution for each image. And there's a cool paper from ICCV that year. It's called S2 wrapper. And we reuse this mechanism to just reuse those features across different scales and across different VIT levels. And again, we can abstract away all this kind of stuff. It's learn projections, feature fusion, blah, blah, blah. The important thing is that if you do this, and if you train this thing correctly, what you end up is with 2 outputs. You get this texture output here with the spatially varying mask, and the subtexture, where you have the individual white parts of the dog selected. Sorry, let me do it like this. And the other thing that makes this work, of course, is multi-level data. Our intern at the time, Julia, she went online and she took a large-scale data set of Adobe Substance materials, 11,000 materials almost, and she randomly combined them with 12 patterns. You can see lesson number 1 maker come back here, and rendered them into 800,000 images, importantly with those 2-level annotations, right? So now we have dense pixel level annotation on 2 levels. And if you have this data, it's relatively straightforward to train such an architecture. And we discovered that it works really well, actually. Here you can see on the skirt the two-level prediction, first the subtexture and then the texture. This works on real-world images. Most cases were resolved correctly. Because of this multi-level processing, you can now resolve fine-grained details. So here you can see the horns of the antlers here are correctly selected in the mask here. And if you have ambiguous cases, like for example this nightstand, where texture and subtexture are pretty much the same, the model correctly outputs the same mask, similar to, I guess, what a human user would do. So this is very useful, as I said, for like editing. You can make edits on like subtexture level, texture level, and so on. Very relevant for Adobe, of course. We're an image editing company. And lesson number 2 is multiscale is important. This is also something that applies to almost every field, whether it's optimization, whether it's rendering. Multiscale always helps. So to recap, we've seen these 2 papers, Materialistic and Materialistic 2. And the lessons learned were it's all on the data and multiscale is important, right? And to remember, in case you weren't paying attention, we're clicking on an image and your output is a selection mask. Now, because we're doing this appearance-based selection, what if I wanted to select all the wood in this image? We said if we have different woods and we click on each wood, we only get a mask specifically for this image. So if a user wanted to select all the wood, they would have to click in all these places, which is arguably not very convenient, right? Wouldn't it be much nicer if we could just say wood, or have like a very simple way of conditioning our selection model? And this is a challenge that we tackled in our internship last year. And this was just presented last Thursday at SIGGRAPH, actually. And it's a project that's called MAOAM, which is the acronym for Mask Any Object and Material. And in MAOAM, this was exactly the problem that we had. You want to be able to support both clicks and text reasoning over an image, because clicks are nice, right? Users are used to clicks. Clicks are very precise, they're very local. We click on stuff all the time, but they're not very good at expressing like spatial concepts. It's very hard to express semantics with clicks. So this is, for example, the advantages that these prompt-based models have. And the goal here was to combine click-based models, click-based selection with text-based input. An additional insight was that materials usually exist on object surfaces. You will seldomly find a material just floating around in space. They're usually anchored to an object. And therefore, it's only reasonable to jointly train from materials and objects to be able to exploit this reasoning together. Here on the left, we had the material selection objects like red, brown wood, dark brown wood. On the spoons, with MAOAM now you can say all spoons or all eggs, and you get all the objects regardless of material variation. So yeah, that was the goal. If you want a model that understands both clicks and prompts and can output materials and object masks, of course you need a unified model that is able to understand all the input modalities you give it. And at the time, what we came up with is this kind of architecture. These are basically the inputs. You have an image and potentially a click overlaid onto the image, and the text prompt. And you have a unified model that produces either the first mask for a text prompt, this one here, for the prompt, can you select the white ceramic in the front, or the second image, if you only click here and you want all the ceramic in the image. And the way this works is by using a VLM. We use a version of Qwen, I think, or it's called GLAM, but it's using something internally, which overlays a star onto an image, and then it embeds the image and the text into this clip space here. So clip is a big model that's doing contrastive language image pre-training. And from there, we have some learnable projections and so on. But this is the load-bearing part, as Claude would say. This is a LLM that outputs a token which conditions the selection mechanism. So this thing gives you this sec token, and the sec token is just a vector of 1024 numbers, but this is the important part because this contains the information that conditions this mask decoder here in the top. And the image goes through like an image encoder. This is a standard SAM model from Meta, with the mask decoder being conditioned by the segmentation token and then outputting those two masks. again, lesson number 1 makes a comeback. How do we train this thing? It's all in the data, but the issue is that we did not have any data that shows this. Like what we need is, not synthetic, but what we need is rendered data, like perspective correct data with text annotations. And if you look online, you can find a bunch of data sets from like SUBRDF maps with text annotations, frontal parallel photos of text annotated materials and so on. But really like this data with annotated materials and mask, we couldn't find much of it. And then we did what you do these days. We asked the VLM to describe these images, and we gave it some masks, and we did some like clever prompting. And actually Jaden spent, like our intern, he spent a long time getting this process like just right. But once he did, we were amazed by the material understanding capabilities of this VLM. It will say things like, made of soft gray terry cloth with orange embroidery. Like these are words that I don't even know, right? And this thing just, you can run this on like 1 million images and it's just gonna do its thing. So this took a bit of time to get it right. But once we did get it right, it worked really well. Like for example, this was the embroidery example that I just gave you. For the shoes, it said like glossy black patent leather with a smooth reflective surface, vibrant glossy green leaves featuring fine serrations. I'm like, okay, sure, right? And then the other thing that we needed to make this project work was a bit of counterfactual reasoning. And if you're not familiar with the term, this is a term from the, I guess, LLM, VLM literature. And it's basically asking the model to really reason about image context by giving it wrong answers and then has to pick like the right one. So this is a task we call VQA, or the literature calls VQA, for visual question answering. And you have, for example, this input image here. And this is what people call a set of marks. So here are all the material regions that we have, and those are annotated, so we have this annotation data, are overlaid with masks and with little numbers. And this helps the VLM to understand better what's what. And this is an example from the training data, right? So for example, we pick this material here, which is this gray wall in the back, and we retrieve the description that we generated in the previous step that I showed you, which says like light beige fabric, uniform patterns, no shading variations, and so on. And then we give this description to the VLM, to another VLM actually, and we say, okay, take this description and generate distractors from it. And they have to be plausible, right? You can't say like, I don't know, red fabric. That would be too obvious. So the VLM has to come up with those distractors. So now it doesn't say light beige fabric, it says smooth light beige wooden planks with vertical grain and glossy finish. And this part that it's in red is actually the wrong part. So all of those are a little bit correct, like smooth light, blah, blah, blah. But they all have some wrong thing in it. And this VQA task you use to specifically train just this first part of the model, the LLM, or the VLM in this case, to really make it do the heavy lifting and code all this information into the seg token, which we can then use to condition the mask decoder. And again, once we trained this thing, we were surprised by how well it works. Like this is from the paper results figure. Here you can see different materials selected by clicks, like we show the clicks as these little overlaid stars. And you can see that it can select like the things on the top, like the rucola, the rocket, and the threads on the cookies, so like very fine-grained stuff. But it can also select very coarse or very like more like semantic things by saying just like brick, metal, gray mesh, black leather, black wood, gray fabric, more like these high-level kind of prompts. And we show the same thing for objects, right? You can show that you can click on things like the giraffes or the background and it will select the correct object, but you can also prompt it to just give you the correct masks output from the prompt. And I guess the lesson here is invest in data pipelines. This took a long time to get right, but once you have those data pipelines, you can scale them easily, and then the rest usually just falls into place, especially with these big models because they're very forgiving, they can compensate for errors very well, and they can extract a lot of knowledge from this data. The next project is a little bit of a curveball because it's got nothing to do with Adobe. It's not by us, but I think it's awesome, so I'm going to talk about it anyway. This is called VIT-MAT, Boosting Image Matting with Pre-trained VITs, was presented at Information Fusion 24. And if you're not familiar with the term matting, this is usually something that's used for green screening in industry if you want to overlay a background onto a green screened scene. For example, here, this is a video from Corridor Key, and you can see how the green screen disappeared. And if you look at closely at like the locks, like this is really, really fine-grained detail that this model gives you, right? So this is a very mature field, many people working on it. The cool thing about this is that they use trimaps. And what a trimap tells you, it's got 3 regions, that's why it's called trimap. The white part of the object is almost certainly selected. Usually the interior, right, is not very hard. The black part is almost certainly background, usually like also not very hard, like even small models can do this very good these days. And the gray part is where you would ask the VIT or the model to refine your selection. So this helps the model to focus all of its capacity into this very thin band and give you very good detail in this specific region. Now, why am I talking about this? Because all the selection model I've been showing you previously run at a relatively low resolution. Like the SAM-based models run at 256, and then the mask gets upscaled to 1024, and MAUAM runs at 512, and then gets upscaled to 1024. Now, if you have an 8K image and you give a 1024 mask and upscale that, you will get horrible artifacts. It looks all right here, but if you zoom in, you can see where the little errors are. This is just not good enough, right, for a professional level. Now, if you train this VIT map thing and tell it, hey, we're very sure that this part is selected, we're very sure this part isn't, so please, please only refine the boundary in the gray region, it actually does a very good job. And you can now run this in a tiled fashion on images of arbitrary resolution. So I think this is a 12K image, and our upscaled VIT map predictions look really good on this task. So the lesson here is delegate subtasks to experts, right? We have a selection model, which is very good at selecting materials, and we have a refinement model, so to say, whose only task is to refine what the selection model gives you. Now, this has pitfalls, of course, right? If the selection model is wrong, this thing doesn't care. It will just refine what you give it. So you want to get your selection model right, but this is the lesson here. And I have about 2 or 3 minutes left, I think. So I want to briefly talk about one last paper. Those were the 4 that we saw, and the lessons. Data is important, multi-scale is important, data pipelines are even more important, and delegate subtasks to experts. And in the last paper that I want to present, we're now going beyond 2D. These were all image-based, and we're going to lift material selection to the 3D domain. This was presented at 3DB this year, actually, where I met Harpreet and the Voxel 51 team. And this is called SAMA for Select Any Material in 3D. So the task remains click-based selection, but now you want to be able to support 3D assets like NURBS, Gaussians, and meshes. And the problem is that 2D models are not 3D consistent. So if you run a 2D selection model on each frame of this video, you can see that the selection is absolute garbage. It's just not usable. So we needed to come up with a way of doing this. And some of the criteria we wanted to support was selection in 3D, obviously, on arbitrary assets, without expensive pre-training. So I want to be able to just receive an asset from the user, run the selection in a couple of seconds and be done with it, and then visualize it in real time. And the insight that we had in this project is that renders of a 3D asset are not so different from a video if you arrange them in the correct trajectory. And we have very good video selection models. For example, SAM2 was just released when I first started working on this project in 24, actually. So we took this insight and we used SAM2 and we adapted to the material domain. And this is, again, lesson number 1, making a comeback. It's all in the data. We did what we always do in these papers. We rendered a bunch of material data. We fine-tuned the model, and now we can select materials. But we're not done yet. Oh yeah, sorry, this is another point. Materials are also videos are also informative for materials because you can see the response to light. For example, here, you can see how the highlight shifts across this metallic surface, and that's very informative for the model. So now we have this fine-tuned material selection model, but it's still just a video model that we run for every frame, right? What if we want to visualize the selection from a new frame? We would have to run this expensive model again, and that's not very user-friendly and a bit annoying. So we had to do some sort of 3D consolidation. And we did this by simply taking those 2D renderings, doing what we did before, selection in 2D. And now because it's an asset, like a mesh or a 3D.js asset, we can simply take those 2D similarity maps and back project them to 3D into similarity point cloud. So this is a point cloud where this heat map is applied to the selection. The click is here on this bicycle, and all the parts that share the same material in 3D are red. It's a high heat map, and then the other ones are blue. And because this is a point cloud now, you can use k-nearest neighbor queries into this point cloud from a novel view to get your 3D selection from a different view that you haven't seen before. And I'm going to skip this one, because this is all on the GPU. It's very easy to parallelize. There are very good libraries for this kind of stuff. And this is a demo of the interface that we had. And this is a new asset. So now we make a click on this brown piece down there, and you can see now the selection is loaded. So click to selection time is around 1 to 2 seconds. And as you can see, you can look at the selection in real time. You can play with it. You can zoom in and out. And it supports all these actions in real time. Yeah, and I didn't really know what to put as a lesson, so I just put in 3D, everything is harder, because you have stuff like disocclusions, you have moving things like specularities, highlights, and so on. Models are not 2D consistent, so you have to be clever and work around this kind of problem. And yeah, that's a small promo video that we can skip in the interest of time. And this concludes the talk, I guess. We looked at those 5 papers. These are the 5 lessons that we learned. Hopefully some of them are going to be transferable to your fields. And what's next? I don't want to spend too much time here. But all of those models, with the exception of my arm, have been discriminative, right? So it would be cool to have a way of incorporating generative priors to be able to better express this uncertainty in materials that we have. This is a low-hanging fruit, extend these models to dynamic scenes and long video. And this is the one I'm most excited about, recursive or agentic self-improvement. Because selection usually is the first expression of intent, right? Once you have a selection, you usually want to do something with it, like edit it, change the hue, change the saturation, and so on. And if you have an agent, and I think we're going to hear more about agents later, once you have an agent that can do this, you can then ask the agent, well, did this material that I wanted to select actually change? And this can be used as a feedback loop to self-improve the selection algorithm. That's it. I was Michael. This is my team at Adobe. Sam, who's here in the first row, Valentin, who unfortunately just left, and then Ilian and Niloy. Come work with us. We're great, obviously. We have a good internship program working on a variety of different stuff. This is just some examples that I brought. We do intrinsic image decomposition. We have a great paper on joint lighting representations, Unilight. You will hear more later about. We do long video generation. We do image editing in intrinsic spaces and so on. And I think Adobe is a cool company at the moment to work for, because on the one hand of the spectrum, you have this extreme level of precision that you get from tools like Photoshop and Illustrator, like pixel level precision. On the other hand, you have this other extreme of crazy prompting, nano banana, make a hat or make a cat, and then change the cat to be blue and add a bicycle and whatnot, which is cool, right? But you don't have any control over it. And I think Adobe is in a good position to bridge this domain and to work at the intersection of these two. So if you do want to do an internship with us, do reach out. We're always hiring. And yeah, that's it. Thanks.